Hello everyone, my name is Sangmin Park from Korea University. This video presents our research title, Debun, Detecting Bundled JavaScript Libraries on Web, using property order graphs. This work was done in collaboration with Sejin Kim and my advisor, Jihyuk Park from Korea University. To begin, JavaScript library open contains security vulnerabilities. As shown here from the vulnerability database, there are numerous reported vulnerabilities in popular JavaScript libraries. For instance, the library named Lodash contain a vulnerability in older versions. Websites using such versions are exposed to security risks. Therefore, it is important to identify which libraries and which versions are being used in the web applications. Several techniques have been proposed to identify libraries and their versions. The first approach is a property pattern-based technique that detects the library by observing patterns at runtime. LDC is a tool that detects library based on manually collected property patterns. For instance, to detect Lodash, LDC checks whether specific property such as underscore and chain exists. After identifying the library, LDC determines the version by reading version properties. Another existing technique is PT detector, which was presented at ASE 23. This tool automatically extracts property patterns in tree structure. However, these existing techniques share a major limitation. They treat the source code as a black box, which can lead to misdetection. So why does PRI treat source code as a black box? The answer lies in the modern web development process. Bundlers like Webpack modify and compress codes together using diverse transpilers. This transformation makes it difficult to detect libraries in the transpiled code and appears in the web application. Here's a concrete example of these challenges. On the left is the original remove function from Lodash, and the right is the transpiled version. You can observe several major differences. First, variable and function names are mangled. For example, names such as index or getIterative are shortened to something like n or an, which makes the code much harder to recognize. Second, the control statements are changed. A while loop may be replaced in a for loop, and multiple if statements can be merged into complex logical expression. This transformation makes it extremely difficult to identify similarity between the original code and transpiled version. However, not everything changes during transpilation. There are two important characteristics that remain preserved. First, property names are preserved. JavaScript allows dynamic property access such as length, so changing property names could break the program. Second, the execution order of property reads and write is preserved. In JavaScript, getter and setter may have side effects. For example, reading obj.p might print 1, while writing obj.q might print 2. Then changing execution order can alter a program's semantic. Therefore, execution order should be preserved. For this reason, most transpilers preserve both property names and their order of property operation. In the previous example, property names like length and push stayed at the same, and their execution order is preserved even though other parts change significantly. Based on this observation, we introduced a new graph called the property order graphs, in short POG. The POG represent both property names and their execution order in a graph structure. As shown here, when we extract POGs from the original Lodash function and the transpiled code, they produce exactly the same graph. We compute fingerprints by hashing these POGs. Remarkably, even when the code looks completely different, the fingerprints remain identical. But unfortunately, there is still a problem that POGs are not always consistent during transpilation. Let me show you three problematic cases. First, flip branch. The branch of if-else statement can be swapped. Second, merged branch. A while loop with a conditional break can be transformed into for loop condition. Last, combine duplicate code. When the same code appears in the both branch, it can be merged into a single assignment. Even though these transformations don't change the program's semantic, they result in different POG structure. Our solution is to refine the POGs using path sensitivity truthiness analysis. In our analysis, we track truthiness of variable along execution path, where a path refers to control flow from each branch. We define an abstract domain with four values. T and F represent strictly truthy values or falsy value, respectively. For value whose truthiness is unknown, we initially assign non-flip and flip alternate with each other through negation. In this left side example, There are 4 paths, and each path has environments that map each variable to its abstract value. Based on this analysis results, we can refine our POG and can solve the problem shown in previous slides, so then make POG more consistent. The detailed refinement process will explain in research paper. Based on consistent POG, we construct system named Debun. Debun operates in 2 phases. In phase 1, we collect various versions of libraries and generate POG-based fingerprints for each function. These fingerprints are then stored in the database. In phase 2, we crawl target website JavaScript code, then generate POG-based fingerprints, finally match them against the database to detect libraries and their versions. The evaluation was conducted using 78 libraries on 68 type websites for 3 research questions. First, we compared our library detection performance against the existing tools, LDC and PT detector, based on the F1 score. Our approach achieved improvements of around 25 percentage point over LDC and 39 percentage point over PT detector, with an average detection time of around 1 second per website. In addition, our methods successfully detect 99 libraries and 125 libraries than LDC and PT detector failed to detect respectively. Second, we evaluate version detection performance. Since PT detector does not provide version detection capability, we compare our approach only with LDC. Compared to the manual to LDC, our method achieved an increase of about 22 percentage point in F1 score, and additionally detect 52 versions that LDC could not detect. Third research question is ablation study related to our analysis-based POG refinement. Detail will be explained in our research paper. This concludes my presentation. You can access our artifact and video using QR code. Thank you for listening to my presentation.